Okay, expert case with the UNIMAP 2023. The title of the register is Overlapping Chromosome Segmentation Using Machine Learning with Test Time Augmentation. I'm the inventor Hariyanti, together with others from USM and also IPPT USM. I want to talk first about the introduction. As you can see, the title is machine learning. If you know machine learning, for example, like you want to teach a baby don't know how to talk and walk, and that's how we train them from their born. We teach them how they need to walk, how they need to talk, and everything. So that's how we actually um, teaching the baby, which is teaching this model, and train them how to recognize our features in the picture. So my project is overlapping chromosome segmentation using the machine learning with the test time augmentation that use the UNet. And as you can see, healthy human cell contains 46 chromosomes. The first 22 pairs of chromosomes are called autosome, and the 23rd pair are sex chromosome called X and Y. Karyotype is the main method used to identify and evaluate the size, shape, and the number of chromosomes in body cell. And during the metaphase, chromosome is aligned on the metaphase plate in the middle of the cells called the centromere. As an introduction, an effective human metaphase chromosome analysis system can be used by doctor as a second opinion during the diagnosis. The main challenge in chromosome segmentation is the separation of the overlapping chromosome, which is the one I look forward. And this study investigated how the test time augmentation with a suitable number of unit CNN layers can improve the design for the semantic segmentation problem. The proposed architecture was trained, validated, and tested with 13,424 greyscale images with 88 times 88 pixels of overlapping chromosome pairs to match the pooling layers, yeah, of course. Okay, and a lot of related works are on this. For example, like Pommier, Gauche, and also Hugh et al. The one that I use to match my result here. And as you can see for the methodology part, you can see that there are a lot of losing information due to no padding. So the implementation model is modified based on the UNet architecture constructed by Olaf et al. So I kind of modify the basic network architecture model, and the paths have two paths, which is constructive path on the left side, which is also known as downsampling path, and also the right side we have a symmetric expanding path for precise localization for classes, which is also known as upsampling path. So this network is very famous, and when we try to modify it's very hard because it's kind of already perfect, but then we figure out how to do it with a lot of modification. In order to localize the high resolution features from the contracting path are combined with the upsampling output, and for that CNN layer can learn to assemble more precise output. The padding is to add extra pixel outside the image, and the zero padding means every pixel value add is 0. Okay, the cropping was not done within the network because the given small input image and undesirable to remove the pixel. For the proposed method, the repeated convolutional network is reused in the contractive path. The network is categorized by the repeated application of two 3x3 unpadded convolutions. Each convolution is followed by a rectifier unit and 2x2 max pooling operation and is supported with strike 2. 4 concatenations are performed in this architecture. The architecture of unit consists of two parts which are symmetrical and connected by concatenating the responding upsampling and downsampling layers. The first path builds an abstract representation of the image by iteratively convolving and subsampling the images, and second one creates the target segmentation map by iterative upsampling and convolving the abstract feature maps. As for test-time augmentation, it was implemented in the proposed model by applying horizontal and also vertical image flipping to limit the training time duration. TTA also modifies and multiplies the training data during the training. The augmentation is randomly applied after every epoch, hence an epoch does not look the same as the epoch before because the model have seen the image at the same time twice. So we provide more input on it using the test time augmentation. It's a very good practice. And for that we got a very good result, which is for test IOU range, we have 90.63% to 99.94%, and for the testing accuracy we have 99.66% compared to 99.79% by 99.22% by WHO, which is quite a big improvement. Okay, and for the segmentation result, you can see it's accurate and contain no mislabelling, and pre-processing is not necessary. It's smooth, it's less noisy, and yeah, it's good. The proposed architecture, as a conclusion, the proposed architecture improves the performance of chromosome segmentation in all areas: visualization, qualitative training, and testing IOU and accuracy. With the implementation of proposed method, the training result become more accurate without any mislabeling, and additional pre-processing also become unnecessary, and improved segmentation accuracy of 99.68% was obtained, which was higher than 99.22% obtained using the method of WHO et al. Thank you.